Welcome to Real Analysis P5, Proof Writing Review. Logic gave us the grammar. Now we review how to turn a mathematical claim into an argument that survives contact with another mathematician. A proof is a finite chain of justified statements showing that the conclusion follows from the assumptions. Examples, diagrams, and computer experiments can suggest a theorem. They do not prove a universal theorem, even after the spreadsheet becomes emotionally convincing. For an implication, identify the hypothesis P and the desired conclusion Q. Assume exactly what is given, and prove exactly what was requested. Declare the objects and their domains. A proof about integers may use divisibility facts that are simply false for arbitrary real numbers. For a universal claim, take an arbitrary object from the stated domain. Do not secretly choose a friendly special case. A direct proof starts from the hypothesis, expands the relevant definitions, and moves forward until the conclusion appears. For example, let n and m be odd integers. By definition, n equals 2r plus 1 and m equals 2s plus 1 for some integers r and s. Their sum is 2 times r plus s plus 1. The expression inside the parentheses is an integer, so the sum is even. The last sentence matters. Algebra produced a formula. The definition of even converts that formula into the promised conclusion. To prove P implies Q by contrapositive, prove the equivalent statement, not Q implies not P. This is useful when the negation of the conclusion gives concrete information that the original hypothesis does not. Consider the theorem. If the square of an integer n is even, then n is even. Its contrapositive says, if n is odd, then n squared is odd. Write n as 2k plus 1 and expand. The result is 2 times an integer plus 1. So it is odd. That proves the contrapositive and therefore the original theorem. In a proof by contradiction, assume the hypotheses and the negation of the desired conclusion. Then derive an impossibility. The contradiction must be a genuine logical conflict, not merely an outcome you find aesthetically disappointing. Assume for contradiction that the square root of 2 is rational. Write it as p over q in lowest terms. Squaring gives p squared equals 2q squared. Therefore p squared is even. And our previous theorem shows that p is even. Write p as 2k and substitute. We obtain q squared equals 2k squared, so q is also even. Then p and q share a factor of 2. Contradicting the choice of lowest terms, therefore the square root of 2 is irrational. Contrapositive and contradiction are related but not identical. Contrapositive proves a specific reverse implication. Contradiction aims directly for an impossibility. To prove P if and only if Q. Prove both directions. The two directions may use completely different methods. An integer n is even if and only if n squared is even. The forward direction is direct, while the backward direction is exactly the contrapositive proof we just completed. Proving only the direction you prefer establishes an implication, not an if and only if. Half a bridge remains a swimming lesson. To prove two sets are equal, prove double inclusion. Every element of the first must lie in the second, and every element of the second must lie in the first. For example, take x in A intersect B union C, then x lies in A, and x lies in B or C. Therefore x lies in A intersect B, or in A intersect C. This proves the first inclusion. Conversely, take x in A intersect B union A intersect C. In either case, x lies in A and also in B union C. So X lies in A intersect B union C. Both inclusions are proved, hence the sets are equal. To disprove a universal statement, give one counterexample and verify that it satisfies the assumptions but violates the conclusion. The claim that x plus y squared equals x squared plus y squared for all real x and y is false. Choose x equals 1 and y equals 1. The two sides are 4 and 2. One legal failure is enough. A complete classification of every failure is unnecessary. An existence proof shows that at least one object satisfies the required conditions. An explicit witness is often the cleanest method. A uniqueness proof shows that any two objects satisfying the conditions must be equal. Existence and uniqueness are separate obligations. For example, x equals 3 verifies existence for the equation 3x plus 2 equals 11. For uniqueness, any solution must satisfy 3x equals 9. Hence x equals 3. We have shown both at least one and at most one. Mathematical induction proves a statement for every integer from a starting point onward. First verify the base case. Then assume the statement for an arbitrary integer k and use that assumption to prove the next case. K plus 1. We prove that 1 plus 2 through n equals n times n plus 1 over 2. For the base case n equals 1, both sides equal 1. Assume the formula holds for k. Add k plus 1 to both sides and simplify. The result is k plus 1 times k plus 2 over 2. Exactly the required formula with k replaced by k plus 1. The induction hypothesis is P of k, not P of k plus 1. Assuming the desired next case would make every theorem wonderfully short and completely worthless. Strong induction allows the step to assume all earlier cases up to k. It is useful when the next case depends on more than one predecessor. Good proof writing makes the logical structure visible. State variables, domains, assumptions, and the exact goal. Cite definitions where they do actual work. Justify non-trivial steps. And stop only after reaching the promised conclusion. A proof should contain enough detail for the intended audience, but not narrate every act of elementary arithmetic as a major plot development. The method should match the claim. Move forward directly. Reverse by contrapositive. Force a contradiction. Prove both directions. Or climb the integers by induction. For sets, prove both inclusions. For a false universal claim, find one counterexample. For existence and uniqueness, prove both parts separately. Next, we will use these proof methods to study ordered sets, including bounds, supremum, maximal elements, and chains. A proof is not ceremonial decoration around a theorem. It is the theorem's warranty. Terms and conditions included.